Welcome to your Chapter 12 notes for biology. This chapter is over the history of life. This first video is for section 1 of Chapter 12, and that's over the fossil record. Your objectives in this section are to describe the ways that fossils can form, and also to identify the use of relative dating and absolute dating techniques. Okay, as you can see, fossils can form in lots of different ways. The most common way that fossils are formed is by this permineralization. It's kind of a hard word to say. And that's where minerals and groundwater are going to replace and deposit on those hard structures of something that's died, and it's going to preserve that, but the actual living thing is no longer there. It's really just a rock. You just have basically the form, the shape of that original living thing that's left behind when it's all said and done. In fact, most of the fossils that we find are this kind of fossil. You don't actually have anything carbon left. There's no real part of that living thing that's left. It's usually just the shape, the form, a cast of what it originally looked like. That next kind of fossil is called a natural cast too. Basically more or less the same thing, as long as if I was to die and fall face first in the mud, it would leave a mold of my face, and that could turn into a natural cast. Right? Water could deposit minerals again, fill that mold. You end up with a rock that's shaped like Mr. Morris. Trace fossils record activity of an organism. So you might have some imprints left behind, like footprints, or maybe even like a nest or a burrow could be filled in, and you can see that those were there and that a living thing was there. Amber preserved fossils are fairly unique in the sense that you'd have to be really, really small to get caught in tree sap and have that resin harden and turn into that amber that's going to preserve you forever. So this is mostly for insects and things like that. You wouldn't see any large animals be preserved in amber, but one specific example was kind of the basis of the Jurassic Park books and movies. Right? They decided that maybe they could get that dino DNA out of a mosquito that's been preserved for millions of years. Although it's kind of unrealistic, at least, it is something that's real. You could find a mosquito from the era of the dinosaurs, and in theory there could be DNA in there. It's just unlikely you could do anything with it. The last kind of fossil is that preserved remain. That one's kind of unique in the sense that usually those things wouldn't be really, really old, but you might be able to find, say, a mammoth that's been encased in ice and there's still tissue left behind. In fact, it might look like it just died a week ago. Right? Even though it died thousands of years ago, it can be preserved well enough that you can still see it for what it was. You can also be preserved in volcanic ash. They found actually specimens of humans that are thousands of years old that are preserved in a bog in the mud that encase them there, and it looks like they died not that long ago because they're so well preserved. The two unique ones on this slide that you should realize, or that you should think about, this amber preserved fossil and also the preserved remains. Those are the only two where you actually have the living thing preserved forever. The rest of them are all just rocks. Right? Generally speaking, they can tell you that there was a living thing there and what it might have looked like, but it's not the living thing itself. It's just a rock that looks like that living thing. Okay, when we're talking about fossils, we got to talk about that relative dating. It's something that we talked about before, but we're going to take that another step in this chapter. So remember that relative dating is basically when you have those layers of soil, one on top of another, and you have fossils that can be found in those layers of soil, and you have those basic assumptions that we talked about before. So you have fossils A, B, and C, and you would assume that C is probably the oldest fossil because it's found deeper and below A and B. You would assume that A is the youngest fossil, but again, not always going to be the case because that could be disrupted by geologic processes. You could have an earthquake, you could have a volcanic eruption, you could have even a dog digging up a bone that could make that change. So there's those basic assumptions again that those things that you find below, deeper in the soil, are likely to be older. It's just not necessarily always true. That's not the only thing that we use to determine how old something is, though. We're also going to be able to use radiometric dating. Radiometric dating uses isotopes. Right? So remember that all of our elements that we have up there on the periodic table have different isotopes. It's a different version of the same element that just has a different mass. So you have carbon-14 that you've probably heard of. Most carbon is carbon-12. So it has 6 protons and 6 neutrons. Carbon-14, on the other hand, has 6 protons because all carbon has 6 protons, but it has 2 extra neutrons that gives it a slightly different mass. It's also kind of unstable. So over time, it tends to break down. And that's where these half-lives come in. Right? So if you have this sample of carbon that you're looking at, over time, it's going to break down and it's actually going to turn into something else. And if you measure how much is left of an original sample, you can actually tell how old it is. Right? The basic idea here is a half-life. So it's actually fairly simple. If I start with 100 grams, right, after one half-life, I'm going to have 50 grams left because half of the original should still remain. After 2 half-lives, this is where it gets a little bit tricky, but not really. After 2 half-lives, I should have 25 grams left of the original. The only thing that you have to pay attention to here is that it's not the same amount that's lost every time. You just cut whatever you have left in half for every half-life. So I divided by 2 in the 100, it gave me 50. When I divide by 2 again, it's going to give me 25. I lost 50 grams in the first half-life, but I only lost 25 grams in the next half-life. If I did it again, it'd be the same thing. Divide by 2, you end up with 12.5 grams left of that original 100 grams, and that would be after 3 half-lives. Now again, the importance of this is that if it's something that we've studied and we know a lot about, like carbon-14, if there's only 12.5 grams left of an original 100 gram sample, I actually can predict exactly how old that thing is, how long ago that living thing died. So if I look at this and I see that 3 half-lives have gone by, and I've studied carbon-14 and looked up some values and know that 1 half-life for carbon-14 takes 5,730 years approximately. Then I can estimate the age of my fossil because all I have to do is take that half-life times the number of half-lives that have gone by, and it should give me an approximate age for that thing. So assuming in this example there was originally 100 grams of that carbon-14 and now there's only 12.5 grams, 3 half-lives have gone by. I divide it by 2 3 times, and then I just take my half-life up above here times 3, and it'll give me an answer as far as how old is that thing. And according to my math here, that living thing died 17,190 years ago. So it's a relatively accurate way to tell how old something is. There are limits to it though, because eventually there's not going to be enough carbon-14 left for me to measure accurately. But it works because all living things take in carbon 14 all the time, right? Plants take in carbon dioxide from the atmosphere, and at least some of that carbon in the carbon dioxide is carbon 14. So they're constantly taking that in while they're alive. We take in carbon 14 every day when we eat food. And so we're constantly taking that in, and we should have a constant amount until we die. Once you die, then that amount starts to decrease. But again, there's a limit when you get upwards of millions of years old that there really wouldn't be enough of that carbon 14 left for you to accurately measure, and there's no way you can tell how old that living thing is. But it is a pretty useful thing for us to look at things that aren't all that old and give a good estimate as to how long ago it died.